Hi, welcome everyone. Thank you so much for attending today's Rodel Overview webinar. I'd like to introduce Rodel's exclusive trainer, Mark Johnson. Mark is Principal Engineer of MTJ Roundabout Engineering and has 20 years of traffic planning and engineering experience, with 18 years focused on roundabout design. His career in public sector engineering work includes 4 years at the City of Loveland, Colorado, and 4 years at the Wisconsin DOT, where he was a key contributor to the WISDOT Roundabout program. Mark has published numerous papers on roundabout application issues and is a co-author of the 2010 FHWA Roundabout Guide. He's also an authorized FHWA peer-to-peer roundabout reviewer and is an active member of both the ITE and TRB roundabout committees. And now I'll turn it over to Mark.
All right, great. Thanks, Kathy. Got a few people still arriving, but it looks like we have about 80 people sign up, and looks like we have 35 signed on currently. So I've broken today's webinar up into 4 primary sections: an introduction, overview,
What's it?
if you would, actually, everyone, if you wouldn't mind muting your, that would be fantastic. So we have an introduction. We're going to look at just the program user interface as an overview, inputs, outputs. We're going to spend a fair bit of time on validation and accuracy. It's an important component of having understanding and ability to know if your recommendations and analysis are sound. And then we're going to look at a few case studies using Rodel and what we're being able to do from an analysis perspective. So Rodel it has a seamless integration of both the HCM and the geometric-based models. It's fully compliant with HCM procedures and practices. This is, something that is important to note. We'll look at it a little bit more here. Rodel implements time-dependent queuing theory, which is the same thing as the HCM procedures that was developed by a US researcher some decades ago. One feature of Rodel in its geometric model, it implements something called high-definition queuing theory, which gives you accurate and stable predictions for queue and delay at high volume to capacity ratios, VC ratios. And that's something that is a separator for Rodel's geometric model. So as I mentioned, we're going to go through looking at US capacity data as compared to the, everyone please mute your phone, if you would please, that would be great. We're going to look at, spend a fair bit of time looking at US capacity data as compared to Rodel's predictions. Rodel includes crash prediction models, both US and UK crash prediction models, which enables the ability to both predict crashes, injuries, and PDOs, and then develop economic analysis from those user costs to include delay user costs as well as the costs associated with the crashes. Rodel, the geometric model allows for modeling single lane to complex roundabouts, flared entry designs, as well as explicit modeling of right turn lanes in closely spaced intersections. I'm just going to note again for those of you who just signed on to please mute your phone on your end, please. Rodel's interface is developed to facilitate understanding of the analysis and explore design envelope for potential solutions. So it uses explicit numerical values. There's no unknown factors. It informs the analysis and design designer of the geometric and operational relationships. It has an interactive and educational user interface. It includes sensitivity testing. You can increase or decrease traffic per leg. This allows for testing of different growth scenarios. Excuse me. Allows for testing of different growth scenarios. It can allow you to calculate life of projects, how long will one lane work, etc. You can also restrict capacity or increase capacity due to context, to include, things such as on-street parking, a test for the inherent variability in driver types. This allows you to check and assess for unacceptable queues or delays. You may have check for upstream queuing and things of that nature that may be problematic in one situation and may be acceptable in another. So traffic planning, you can have, there's a planning level where you can actually specify operational parameters for delay or queue length or VC ratio, and then it'll give you sets of geometric parameters to meet that targeted parameter. And then the full geometric analysis can allow you to refine your geometry and do bypass modeling, model for capacity effects. As was mentioned, it's fully compliant with HCM. They both use time-dependent queuing theory, so nothing in this respect is different from Rodel geometric model versus the HCM model. Delay is derived from queuing equations. Rodel incorporates high-definition queuing theory, which provides stability over the entire range of VC ratios. So this becomes quite important at end-of-life scenarios when we're trying to decide on our laneage of 1 versus 2 or 2 versus 3. Having a solid understanding of queue and delay at those high VC ratios is a key important feature of the geometric model. It allows you to model different types of roundabouts: smaller, compact, single laners; larger, more curvilinear single laners will give you different capacity. Same thing with multi-lane designs. You can have a wide variety of types of designs, and Rodel will account for the operational effects of those different geometrics. Bypass lanes, you can have full, it models full right turn bypass lanes, or free right turn bypass lanes, as it can be called, or yield right turn bypass lanes as well. And everything, it allows you to have, as you know, we can have different traffic patterns. You have different types of entries: flared entries, right turn entries, full 2-lane to 2-lane entries. So Rodel can model all those different scenarios. This is a flared entry design that is one of the strengths of Rodel, allowing for the modeling of the approach roadway width, the entry width, and the flare length over which you are widening from that single lane approach to a 2-lane entry. You identify the laneage in the Rodel in terms of how many entry lanes, how many circulating lanes, and how many exit lanes. A couple key features and improvements over the last number of years includes, and more recently, the online support to include free tutorials, as well as support plan that includes easy to follow how-to case studies to accelerate Rodel proficiency. Much of the information that I'm talking about today is available online in these free tutorials: the introduction, basis of program, validation and transferability, and as well as a program interface, a quick start guide. The support plan, which provides an annual support plan to include updates, as well as access to case studies to go from single lane to flared entries, bypass lanes, exclusive left turn modeling, HCM 6 calibration as well as a few others coming soon. So next we're going to just do a overview of the interface. So this is the main screen of Rodel. This first just is the project information, includes your model types, put in the type of you could just put in your type of project, what models you're using. AM, PM is up here, your year, and those sorts of things. You select the type of model. Geometric model is selected here, and then the geometry inputs are there. Your traffic inputs are the next row down, and your results output field is the third row. And so this is the the user interface, in that you put in your geometry. In the case of the geometric model, we'll look at the HCM model in a moment. You input your traffic flows and your truck percentages and your peak hour factor and any other, and this is where the factor is for volume modifiers here. And then the results is down below. You have your typical results, and you can select your 15-minute results, which would be consistent with HCM and procedures, or you can look at the average over the entire hour as well with Rodel. Your typical output gives you your flow rates, your opposing flow, your capacity available for that traffic, your VC ratio, your average delays. One additional output that Rodel provides that's different from other programs is it gives you if you're looking at a 15-minute result, it gives you the peak 15-minute queuing, your average queuing, if you will, during that peak 15 minutes, as well as the 95% queuing, which is more typical that we're used to seeing. So in the capacity model, with the capacity model selected, nothing changes. It's the same screen, except for you see now in the geometric row, you just select your lanes, and it will also show you if you're using calibrated or default values here, and we'll look at that in a moment, how you turn those on and off. So again, your traffic doesn't change, your results output is still the same place. So you can toggle back and forth between the models within the program, which is a nice feature. Secondary inputs are available here, the calibration tab, the accident tab, economics, and bypass tab, and we'll look at a few of those here. So you can calibrate within the geometric model. You can learn about how to calibrate. At this time, we're not recommending any calibration. The geometric model, as you'll see in one of the next sections, is quite accurate for US predictions, but those capabilities are available. And then within the HCM model, you have the choice to select the HCM 6 model, and you can also use the HCM 10 model, which is, and you select which model. If you're in the HCM 6 model, it has the default values listed here. You would then input your calibration for your follow-on times in here for the different types of scenarios: a 1-to-1, a 1-to-2, a 2-to-2 lane, and a 2-to-1 lane, consistent with the HCM. And then you would select. If everyone could please make sure to mute yourselves, that would be fantastic, so we don't get any feedback. Thank you. Then once you've inputted your calibrated values, it will save those values for whatever calibration values you'd like to use, depending on your region, area. And then you select, for example, here I've selected the calibration values for this leg, and then in this particular case, I've left the HCM default values for the other 3 legs, just as an illustration. The primary calibration values for HCM6 is the follow-on time, which is shown there. Rodel is also implemented if you wanted to. There is an effect on the critical gap as well, and if you want to use that, you can use that. It's slight, and the HCM6 dropped it as a calibration feature, but it's available if you want to use it. If everyone can remember to mute themselves, please, that would be great. If you can just check, there's a mute button on your screen. So bypass lanes, one of the features Rodel has incorporated is bypass, which includes free bypass lanes, sometimes referred to as a full bypass lane, as well as yield bypass lanes. So you can model different types of yield bypass lanes. And we'll look at, and this is in the child menu where you, one of the secondary menus here under bypass lanes, where you select the type of bypass lane, as well as the geometrics for that bypass lane. And so we've gone ahead and incorporated in the manual, examples on what inputs go where and what is what. And I'm just going to go through these just kind of rapidly that show some of the different types of bypass lanes and the inputs that you can find in the online manual, as well as the case study tutorials. So some of the basic, and then your continuous or free right turn lanes as well are available. So in accidents, in economics, something that Rodel allows is you select a crash model, and you can choose the US model or the UK model, or a combination of the US 672 model with the UK pedestrian crash model as well. And you can analyze for crashes, for different types of crashes, both PDOs as well as injuries. You input in the economic data menu, you input the cost per delay goes up here. So you can input a cost per delay and it'll give you costs in your economic analysis. You also input costs for the types of crashes, fatal, incapacitating and non-incapacitating, as well as property damage only crash costs are put in there. And then you would, these percentages are also input, and it'll give you the output. It'll give you the types of crashes that occur, which is approach crashes, entering circulating, exit circulating, and then all crash types, as well as the PED crash types are output, as well as you can get those in rates, as well as just the pure number of crashes. And then, of course, the associated costs with those will be calculated as well. Slopes and intercepts, you can look at the slope and intercept of your capacity lines within Rodel, your y-intercept, your x-intercept, the slopes, which gives you a good feel for things, which we'll look at some of those in the next section. Again, your accident report, accident rates, as well as your user cost, to include crash and delay costs, are all calculated in there, annualized per year. And then you can get global output for everything as well. Rodel includes embedded pop-ups, which can be useful reminders on what things mean which comes in quite handy as you're getting to learn how to use Rodel, or if you put it down for a number of weeks or months and come back to it, as well as the online user manual that you can click through to also find information in more detail. There's some error messages that you can get. For example, this is one that's common if you're toggling back and forth between the geometric model and the HCM model. The HCM model, it'll just tell you, like here it says leg 1 must have 2 lanes. You're feeding a 2-lane entry to a 2-lane circulating, so it's letting you know you need a 2-lane circulating there. Number of okay, so that was it for the overview of the user interface. In this next section, we're going to be talking about Rodel's basis and its validation for U.S. conditions in terms of its accuracy for the U.S. And lots of this information I'm about to present is I've written a number of papers, and we put them into posters for various conferences, and those are listed on this first page here that are available on my website for anyone to download. Most of these are also available on other, like the Teach America website, and or through TRB directly. So as most of you know, or maybe many of you know or may not know, I mean, Rodel's geometric model is predicated on UK research that was published in 1980 based on a significant amount of analysis and research over a full range of roundabout geometries and traffic volumes. They rechecked their equations periodically. In 1995, they found them to be very accurate and stable with no changes required. That stability is attributed to the large statistical database that was collected, again, over that full range of traffic and geometry. So let me get this into presentation mode. And so what they did by using the geometry, and they diverted from their the gap-based methodologies, and they went directly to understanding performance as well as safety based on the geometry. And they used they started with 35 geometric parameters, and they did the regression analysis first to 16 and then finally to 9 of the statistically valid programs. And the 3 major capacity variables are entry width, approach width, V, effective flare length, L, and then the minor capacity variables of radius, entry angle or phi, and then diameter. And diameter only has effects in higher circulating flow conditions, so it's not particularly that sensitive in many cases. So there's the flared entry design again that we saw earlier in the variables, and a flared entry design. So validation. One of the issues that's sort of been challenging for the geometric model within Rodel is when we started doing capacity research in the U.S., the data that was used to develop the 2010 HCM, the data that they used, they reported that that international models were over predicting capacity, and I've spent a fair bit of a lot of time looking at this, and we're going to look at that together here in a moment. And then again so in 2010 they came out in about 2005 and said that it was over predicting capacity, and then recently the HCM6 update based on the 2012 data that was and research that was conducted for the HCM6, the 2010 update, They reported they couldn't find geometric sensitivity, and they also indicated that the exponential line provided a better fit. And these findings all seem to imply that that the UK geometric model perhaps is not accurate or valid for US conditions. As we dig into it deeper, we find actually just the opposite. It matches very closely to US conditions. So in the original 2005, when they reported over prediction, you know, it fit a nice narrative that UK drivers are more accustomed to roundabouts, possibly smaller or smaller cars and those sorts of things. But what we find is they misused the program, and they put in actually a width for a flared two-lane entry. And so the actual capacity, I have this set up on timer. Let me just go back and show this real quick. So they reported 1,800 vehicles capacity, and that's they put in essentially a 20-foot width, and that was just for trucks. So they confused a widened single lane entry for trucks with an actual flared entry design, which was what Rodel was modeling. And so when you actually look at the capacity prediction, it's 1,800 for a flared entry design, and the UK data is dead on essentially with our US data, very close to our US data at about 1,000, 1,100 y-intercept is what they were finding in the UK, which was what Rodel was originally predicated on. To avoid the misuse, the 2012 update to Rodel included the lane-based methodology, which avoids the overestimation of capacity based on incorrect use of the program. So the bi-lane inputs develop your effective geometry for you. Some of the things that we were finding in the more recent data is a wide spread of data, and so we started looking at that pretty closely. And when we segregated the data by geometric types, we were able, and then we compare Rodel's geometric capacity line to a smaller single lane roundabout to a larger, more curvilinear style single laner. We find the geometric model is able to better predict the capacity for those two different types of roundabouts. And so that gives us a lot of confidence in the predictive capabilities of Rodel. We went through, and this is a little out of whack here. Let's see if I can get this. Oh, there's the HCM. Apologize for that. So we find that essentially Rodel is matching, the geometric model is matching the US conditions very well. Of course, sometimes researchers they don't quite understand the relationship between design and operations. So if you have a project where a researcher may go out and measure a two-lane entry, and the queuing is very long and the delay is very long on one lane, as you can see by this photo, everyone's using just a single lane. And so that's because of the geometry of the roundabout. So you have to have effective geometry, and understanding those relationships is important. So no matter what program you were using here, the field measurements wouldn't match very well to the prediction of the program. And it can become more subtle as well in terms of underutilization based on misalignment issues, geometric issues, as well as signing and marking issues can have an effect on that as well. And so these things all make the research side more complex than sometimes is realized. This is a project that has heavy queuing in one lane, and it's difficult to know why people aren't using both lanes here. But as you look at this project, some of the signing and marking is not particularly very instructive, and so drivers go with what they think is going to get them to the right place and so you get poor lane utilization. As was mentioned previously, the 2012 data for the HCM6 or the 2010 update, now called HCM6, they couldn't find geometric sensitivity, and part of the challenge was the widespread in data that they were using, and they wanted to have a calibration feature and to the follow-on time only on the y-intercept. And so, but when you look at the data, they ended up averaging the follow-on times and then anchoring the intercept up at 1380 or 1385. I think it's 1380. And but the actual intercept of the data is closer to about 1200 without using the average follow-on time. And so that's a more accurate fit when you don't use the global follow-on time. And then as you compare different things, and this is written up in a recent paper that we submitted for TRB 2018 in a lot of detail, but at the end of the day, what we find is that the Rodel capacity line fits very well, and the background and need to kind of understand this at this level is when you're toggling back and forth between the HCM model and the geometric model, or you're comparing Rodel's geometric model to other HCM or other programs such as Sidra in HCM mode or in standard mode, you get different results. And understanding the fact that you're getting different capacity lines and you get different results depending on where you are. For example, here's the HCM 6 capacity line shown in red, and at a circulating flow of 950, you can see that the capacity is quite a bit lower than Rodel's capacity line, and so it's going to predict higher delay and higher queuing and or a call for an additional lane or more capacity compared to the Rodel line, which is shown there. So in this case, this is a project where the HCM6 is showing a available capacity of 525 at 950 vehicles circulating, and the geometric model is showing 700. And so you're differing output with respect to queue and delay for a single lane entry in that case, and with one saying a single lane is not sufficient and the other saying it is. And so understanding that this is dipping down below is important. So there's the different types of roundabouts. We found that so we wrote a paper, and I worked with a statistician to look more closely at this issue, and this is a paper that will be available here shortly. It was submitted and accepted for the TRB annual meeting. So again, that wide scatter of data within the single lane roundabouts, and then as we looked into it, we then segregated the data by geometrics, and we could see a very distinct difference in the data for the different geometric type that they collected. So what we did is we used the geometrics from the smaller urban compact style roundabout and then the larger roundabouts that they had as well, and then compared the geometric model to these two types to the data of the smaller compact as well as the larger. And what we found at the end was the Kimber line here is shown in the orange tan color, and the HCM6 in the green dash. The Rodel line predicts better the capacity as we went through that statistically in terms of fit a line, and it out predicts or outperforms the HCM6 line in each case. So this is what this really our summaries of the paper were, that the uncalibrated geometric model gave better prediction than the HCM6 model, either using locally calibrated or with the global follow-on times within the HCM6 methodology. The variation in data is therefore caused by geometric variation, not by different driver types. Again, the good fit that the geometric model provided, the uncalibrated geometric model provided, on the local data indicates that the geometric differences between the sites are the primary cause of the difference in driver behavior between the sites. Similarly, in the 2x2 in the multi-lane data comparing Rodel's prediction to our U.S. data, it's right there in the wheelhouse of our U.S. data, not over predicting. So that's the end of tab 3. So we're going to move to the last tab here. And after this tab, we'll open it up for questions. So intersection control evaluation, formerly, we referred to this as a feasibility study, but the intersection control evaluation is more focused on the operations, but it has very much, like a feasibility study. But so, we're using HCM 10 and 6. Some folks are using spreadsheets. For example, Georgia DOT has their own spreadsheet based on the HCM methodology, CIDRA standard with environmental factors or HCM mode, and Rodel as well with both geometric model and the HCM model. So in general, every state and agencies often have slightly different terminology around their intersection control evaluation process. But at the end of the day, it refers to a process or a framework, to provide evaluation and selection of design concepts for intersections and the connecting roadways. So, we often have an initial screening component to our projects, and one of the things that we want to, be careful is we're not screening roundabouts out prematurely or providing over design that may affect their performance as compared to other intersection types. So having an accurate program or analysis and or utilizing multiple tools to include HCM and the geometric model within Rodel to compare and look at things is important. And then we go into more refined analysis, more engineering analysis, which can as long as it didn't get screened out, include more safety and geometric analysis. So Rodel can help support that as well in terms of the safety analysis, the economic analysis, trying to tie geometrics down more accurately as well in terms of impacts and costs of construction and or environmental impacts. So at the end of the day, understanding the problem that you're trying to solve, identifying potential solutions, and it's an optimization process. And so Rodel facilitates an understanding of the analysis and the geometric relationships, and can help you identify potential solutions to evaluate. So looking at a couple of case studies here. A project that was initially analyzed with, in this case, CIDRA. As we looked at it in Rodel with the geometric model, the original plan was for a project that has 2- and 3-lane entries with some right turn lanes. So you still have 2 circulating lanes in this case. So it had 19 conflict points in this case. In looking at with Rodel and refining that, we start looking at, well, what else might work here? And what we identified was that the VC ratios were high. With Rodel's high definition queuing theory, we're able to understand the queue and delay at the high VC ratios and understand, how necessary all that laneage may or may not be based on that long range projection. And so we identified really what we termed an interim design, but the Rodel in this case showed that this would likely provide adequate level of service on that long range flow. And so from a decision making process, it was easy to implement the interim condition, knowing full well that the ultimate may not ever be needed. But so we're able to reduce the conflict points by around 42%, which is pretty substantial. What we're finding is that that macro level conflict point reduction substantially improves safety for all modes. So then we went, as you further refine the design, this is quite a ways along in terms of identifying an interim and ultimate design. Here's a project in looking at a number of roundabouts in a very constrained, high volume condition. The initial analysis showed 98 conflict points. When you look at all the roundabouts and add up the laneage, 3x2 entry, 6 conflict points. When you add all those up, it had 98 conflict points. When we went through with the Rodel, with the geometric model, we were able to reduce the laneage pretty substantially, and we cut the conflict points down by 48%. So that's going to not only improve feasibility, improve safety, it's going to allow for potential less impacts as well as you move into more of a design stage. The Rodel allowed for modeling quite accurately the flared entries and the closely spaced condition that we had on 2 of the very closely spaced roundabouts, allowing you to have a good understanding of your operational effects. Here's a project in another project. Oh, let me open that up. Similar to the previous project, understanding what's going on here. Let me try that again. So this is a project that I did a review on and went through operationally using Rodel's sensitivity analysis tools. One thing that I do often is, after I've gone through and have a good understanding of the traffic from, say, build year to design year, have a good feel for how much growth is built into that long range design. I may do some sensitivity tests, and Rodel allows you to easily just reduce the flow on a leg. So what happens if I reduce the flow by 5%? In this case, there was nearly 60 to 80% of increase from build year to long range. And so what we're able to do is quickly identify the fact that the 3 lanes on some of these entries were likely not necessary, and pointed out that there's going to be substantial over-design for near and midterm and likely long-term or potentially long-term as well. And so as we go through that and look at that, we're able to, at a concept level, reduce with that 5 to 6% reduction of traffic, identified a 33% reduction in conflict points. So we're able to reduce the laneage. That's going to improve safety for both vehicular safety as well as non-motorized users as well. We had a 25% reduction in PED lane conflicts. It allows for improved speed control opportunities as well. So, understanding the full context of the project, this, I guess, just going through and understanding where some of your growth is coming from. Rodel has features you can understand your queuing and delay through the course of your peak hour as it as you use that peak hour factor, the traffic builds up, and you can understand your queues and delays through the course of the whole hour, and provide you a better and more robust understanding of the situation. And so I know I went through a lot relatively quickly. It's the point of the overview to point you to resources that are available online with Rodel, point out some of its key features, at this point, I'll go ahead and if there's any questions, you can unmute yourself, or you could text them in the chat box, and I'll try to answer them. Someone must have at least one question. Well, we'll wait another minute here. If there's no questions, we'll go ahead and end the webinar. I guess what I can say is we'll likely make this available and send it out an email to everyone in terms of the recording. Okay, well, if there's no questions, I'm going to just hand it over to Kathy. She's going to just conclude with a few comments. Thank you very much.
Thank you, Mark, and thank you again, everyone, for participating today. Just a couple of reminders that all of our online training modules are available with the case studies on the Rodel website, and we will be sending a very brief evaluation form and would greatly appreciate your feedback for future webinars. Thank you again. Have a great day.